Hello, today we're going to learn about binary expression trees. Binary expression trees. So we're going to learn what they are and how we can use them. So I want to get started right away just with a very simple postfix expression. 5 space 7 3 minus times. This gives an opportunity for us to review how to evaluate something like this. We would typically use a stack, but we know that the operators come after the operands. So 5, 7, 3. Okay, then minus. Well, that means I need to subtract the 3 from the 7. So that'd be 4. Then I get a times, so I need to times 5 and 4 and get 20. That's how that works. So infix notation for this would be 5, and then we're doing 7 minus 3 like this, and we're going to do that first, and then we're going to times it. So you'll notice when we switch from postfix to infix, we now have to introduce parentheses, and that's the problem. Another word for postfix, by the way, is called reverse Polish notation, because it's reversed, and it was Polish person that did it. So another type of notation is called infix. Now, prefix. So this is postfix, and now this is infix. Now, prefix is where the operators come before the operands. So we're going to times last, so I'll put that one there, and then we're going to do what I'm going to be timesing. Well, I'll be timesing a 5 times the subtraction of, let me pull that over here. I'll be timesing that by the subtraction of 7 and 3. Okay? So we would, you think infix can be confusing to think about, but you have prefix can be kind of tough to think about. So you have to say, okay, I'm going to be multiplying what? 5 and what else? Well, I'm not going to tell you yet because I'm going to be subtracting. You're going to be subtracting what? 7 and what else? 3. Now I've got that. Then I know what to times by 5. All right, so let's go ahead and make a binary expression tree from this. So the way this is going to work is we're going to start with what we do first. The first thing we do in this expression is subtract 7 and 3. So I'm going to make a node called subtraction, and what I subtract the 7 and I subtract the 3. Once we get that result, then we're ready to multiply. So I'm going to put multiply right here. And what I multiply it with is the 5. And I'll put the 5 on the left-hand side since it was listed before the 7 and the 3. It'd be algebraically equivalent, but this will make it match. So this is our binary expression tree. So what would this tell us? Well, let's take a look at the pre-order traversal. Okay, pre-order. And we could review how to do that. We'll talk about those algorithms later. You can review them from the previous video. But the way that we can figure out what a pre-order traversal would be is, remember, you start right here on the left of the root node. And to get the pre-order traversal, it's everything if you can touch it on the left. So if I can touch the left-hand side of that node, then I'm going to write down that node's value, that data. And then we always move around and to the left. So I come over here. Well, I can touch the left-hand side of the 5. So I'm going to put a 5 next. And then I'm going to come around here and I can touch the minus, right? So I'll put the minus. And then I'll come around here and I'll take the 7. And then I'll get the 3. Well, there we have it. Well, this is the prefix notation. So what we see is pre-order gives us prefix. Now, we've learned about how to write the shunting algorithm to put something in postfix. We've used a stack in order to evaluate postfix notation. Well, you can also use our data structures to evaluate prefix very easily. So a computer can evaluate prefix just as easily as it can evaluate postfix. So this is a perfectly reasonable expression. We know that this value should be 20. This is saying times 5, 7 minus 3 is 4, times that with the 5, you get 20. So that's what that does. Well, let's take a look at what the in-order traversal would do. What would in-order do? All right, let me just erase that. And I'll use the orange this time. So in order, remember, we have to be able to touch the bottom of our node. So we can't just start with this times. We have to touch the bottom half, and we can't. The rule is you can't go through a line. And this is just kind of a neat little trick to help you know what the traversal would give you, right? So we're going to go around. We're going to have to start here, but we're going to have to go all the way around. We can finally get the 5. Okay, so here's the this is in order. Okay, so in order gives me a 5, which then gives me a times, right? Which then gives me a 7, okay? Which then gives me a minus, okay? Which then gives me a 3. So you can see that in order actually gives me the expression with, infix notation, as we call it. What's missing? Well, what's missing is the parentheses. So you'll notice this doesn't work, right? This can't be evaluated because it misses the parentheses. So we'd have to do some extra stuff there. We could use the level of the tree itself to tell us to use parentheses. Well, we're just going to have incomplete in order notation in this assignment because it's not, computer can't really do it anyway. Computer needs in prefix or postfix. Infix, no good. All right. So let's go on now and let's do the postfix. And I bet you can imagine what that's going to do, right? The post order traversal, what it will do. We know that post order we have to be able to touch the right hand side. So I start here, I go all around. I can't hit the 5, so I'll put that down. And then I can come around and hit the 7. Okay, I got the 7. And I can hit the 3. I got the 3. Then I got the minus. I got the minus, and I got the times. I got the times. So you can see that this expression tree can put it in infix, postfix, or prefix just by using in order, pre-order, or post order. Just a really cool application of our 3 traversals, 3 depth first traversals that we've been studying. So let's talk about how do we make an expression tree. All right, you're going to be practicing again using your iterative algorithms to do that, not the recursive. Okay, you do need to know the recursive, of course, but we're going to be using the iterative, which works really well when you have to return something. But let's talk about how would I do this. Well, we're going to start with a postfix expression. If we didn't have a postfix expression, we'd probably have to use our shunting yard algorithm to Dijkstra's shunting yard to convert it. And we remember that's a lot of work, right? Fun algorithm there, but we're not going to do that. We're just going to start with it in postfix. Okay. So how do I make a tree that matches this? So let me see. I've got the algorithm here, and I want you to see it on TV. Okay. So there it is on your phone or wherever you're looking at now. This is the algorithm, okay, and I'll include that, of course, in whatever assignment I give you. But this is the algorithm, all right, and I'll go ahead and be following that. So the first thing we have to do is we're going to make a stack of nodes, okay. Now that's what it's typed as because there'll be references to nodes, but believe it or not, these are actually going to be trees. We're going to be making a stack of trees. Isn't that cool? All right, so we're going to loop through this. For each element in the postfix notation, if it's an operand, okay, we'll simply push it on the stack. Okay, I have to create a node, but we'll push it on the stack. So 5, all right, that's an operand. We're going to make a node, okay. So I'm going to call new node, right? With that 5. So whatever. So I'm just going to write down 5, but understand that it is a node of a binary tree, so it has a left and it has a right. Okay? All right, let's do the next one. The next one is an operand. So if it's an operand, you just put it on the stack. 3 is an operand. You put it on the stack. Okay, minus is an operator. So when you come to a minus, okay, we make a new node with that operator, but then we pop. We're going to pop these 2 things off of it, okay? So the 7 has to go on the left. So the first thing I pop becomes my right child. So I'll assign my right child. Remember, this node's part of a binary tree, so our node class. We're going to have a private node class that's nested in there. It's going to have a left and a right, and probably a string value or data, right? So we're going to put the 3 there and then the 7 there, okay? And believe it or not, that's what's going to go here. We popped these off, they're gone. And so what goes there is this. How do we put that in there? Well, all we have to do is put a reference to the minus because that's my root. But I'm just going to say that basic. So the only thing that's there is a reference to this node here, and then the other references come along for the ride. But you can think of that as what's being in my stack right now. Okay. All right. Then what's the next thing that comes off? All right. Well, the next thing that comes off is a times sign, right? So we just got a times sign now. I want that white. I want you to be black. There we go. So remember what we do when we get an operator. We take the operator and we pop. What we pop off first goes on the right. And when I attach it to this reference, what I'm doing is I'm just connecting that node to this node. And now I've still got the 7 and the 3. And then I pop off that node, and that's a 5, and that goes right here. Pretty cool, huh? I'll tell you what, let's do one more. So let's take a look here. What would be another one I could do? Let's do another one from what will be our assignment. All right, this will be a longer one, but so hopefully it'll be worthwhile to kind of see some of the nuances if there are any. But it's not too bad an algorithm. It's not too complicated. All right, so we're going to use, let's see here, 2, 3 plus 4 times 3, 4 minus divide. All right. So if I find an operator, or if I find an operand, I just make a node, which I'll show with a circle, and I put it on the stack. Okay, I got another operand. All right, we got a operator. So then I pop. The first thing I pop goes on the right. Second thing I pop goes on the left. All right, so those got popped off. They're gone, and they're going to be replaced by this guy. All right, what's the next thing? Okay, we got another operand, so 4. But then we got an operator. So I've got this times sign. First thing I pop goes on the right. Second thing I pop goes on the left. And what this is going to link to is just that plus sign, but that plus sign, of course, has the link to a left child and a right child, right? So those are gone. And we push this back on the stack. So after we pop and assign, we push back on the stack. That's important. All right. Okay, what's the next one? We have... we just did times, right? So now we have another 3. That's going to go here on my stack. Then a 4 is going to go on my stack. All right, then we got a minus. So when we got a minus, we make a node. We pop from the stack. So I pop off the 4. I pop off the 3. Remember, you assign it right, then left. And guess where that goes? Right back on the stack. You got to push it right back. Okay. That was the minus. Okay, last we got to divide. So what do? We make a node. Right child becomes this. Left child becomes this. Okay. Well, hold on. Let me move that over. There we go. So that goes there, and that goes there. And lo and behold, we got ourselves an expression tree. Check out the postfix order. The postfix order would be 2, 3 plus 4 times 3, 4 minus divide. But now you can get infix. And in fact, if somebody told me, I need you to put this in infix order, like I would... Infix is really difficult for me to just do, even if it's... So if it was... someone gives you something... Not infix, I'm sorry. Prefix is really difficult. Someone gives me something in infix or postfix, I would take any infix, I put it in postfix. That's easy. And then I would make this tree out of it. And then I would go, all right, here's my infix. Divide time... My prefix, excuse me. Divide times plus 2, 3, 4, 3... Sorry, 2, 3, 4 minus 3, 4. That's the only way I know how to do prefix. It's too difficult for me to wrap my mind around it otherwise. Okay, so that's it. That's binary expression trees.